Okay, folks, are you ready to try your answers against mine? Did you get them 100% correct? Did you get them 0% correct? You know what? It doesn't matter. It doesn't matter if you got all 4 of them wrong, because if you did, you're learning, and that's all that matters, right? As long as you do it the right way on the test to show me that you learned it the right way, not memorize. Remember, I hate the word memorize. I want you to learn it. I don't want you to memorize it. So let me clean off the screen, and we'll tackle Part A. All right, so for Part A, it said you're going to take CH3, CH2, CH3 with an OH here, and you're going to add to it HBr. All right. They want to know what the product would be. This is how I do it. Every single time in an organic reaction, if you've had me for Chem 251, you know that I like to start off just rewriting the reagent that we started with. I mean, this is always a good place to go, and that's what I'm going to do here. So let's think about the mechanism here. I have an alcohol. It's very pretty, the OH group. It doesn't want to go anywhere unless, bam, I give it a back black eye. So I need to add HBr, an acid, to that OH group. And that allows it to get ugly, and that carbon doesn't want anything to do with it anymore. And then the OH gets protonated, and then it leaves. All right, so the very first thing that goes on, I'm just going to write it down just so we can kind of keep it in line, is that this HBr will protonate the OH first, and that makes water. This is a secondary carbon. That's what we said in the last video. That secondary carbon is undergoing an SN1 reaction, a substitution unimolecular. It only sees one thing at one time, meaning that unlike in the last video and the previous examples, this water molecule is going to leave completely first. And that allows this carbon to form a full carbocation. This did not happen in the last one, right? In those last 4 examples, carbon was a big cheater, and it saw 2 things at one time until he made up his mind on which one he liked better. Well, in this case, carbon's now single, right? I told you, one thing at one time, carbon ends it, says that was a bad relationship. I need to fix myself first, and this is the fixing step. So this carbon looks left-handed, and that carbon says, you know, this spot is still a secondary. That has 1 carbon to the left and 1 carbon to the right. It's attached to 2. And then the carbon on the right-hand side, this is primary. There's only 1 other carbon, and that's the one to the left. So I don't really make myself better. Okay, if I go right-handed, I'm going backward. Why do you want to go backward in life? You don't want to do that, right? So it's not going to move right-handed. And then if it goes left, it's a secondary, and it's already a secondary. So it says, you know, that's too much trouble. Why do I want to go through the trouble of uprooting everything that I have here, moving to a completely different town or city, going into a brand new apartment or a home, and starting life all over again? No, just for the same amount of paying job? No, I think I'll just stay here and deal with it. So this carbon's going to make the decision of not moving. There is no rearrangement that will take place here. So now we have confirmed that that is the spot that it's going to stay. And in the next step of the mechanism, what happened? Right? We took hydrogen and we protonated the OH group, and that left. And then the very next step is that a new bond came in, and that new bond was with the bromine that we used up here with the acid. So we've just made our alkyl halide just like before. There's no difference here. The slight modification was the rearrangement step. We did not just place it on there and didn't think about where it was going to end up. This is what you have to do. It's very careful for secondary and tertiaries. They will rearrange every single time that they can. So folks, here's the right answer for Part A. The OH was protonated, it left, and the Br is going to go on in its place because rearrangement did not take place. All right, so now let's look at Part B. In part B, they try to trick you up, and they try to give you a ring because they know people don't like rings. They look ugly, they look more complicated, but they're not. Whatever, don't let them trick you. All right, so there's the ring with the CH3 group and the OH group. And then we're going to add on HCl. And we want to know what would form. All right, so using the same thing that we just did in part B, let's do it again. All right, so I'm going to start off with redrawing my reagent. So here I have a CH3 group and an OH group. All right, so let's do them one step at a time. This hydrogen will go on, bam, and give that OH group a black eye. So here we go. That makes that a very good leaving group, and this leaves. Da-da-da-da-da-da, whoop, there it goes. All right. Well, what I have left over now is a carbocation. The reason that I'm doing this is because in the last video, we said that this carbon, folks, was a tertiary carbon. There's one up above, and there's one to the left, and there's one down to the right. So this carbocation's not going to go anywhere. I mean, tertiary is really the best spot for it. I mean, you talk about location, location, location. This carbon's got like a condo on the beach, right? And it's paid for, and there's no rent. Why would you want to move? So the same thing's going to happen to this organic. So that carbocation is on a very good place. It's not going to go anywhere. And that carbon says, okay, I'm ready for a new relationship. What's out there? What wants to come and get me? And the chlorine swoops in and says, hey, I'm ugly, but I'm here. And if you're okay with that, we'll make it work for a little bit. And there's your product for part B. So once again, no rearrangement took place, but we had to at least check it. That's the difference. Again, in the previous video, all 4 of those examples were primaries. Primaries do not rearrange. They cheat. They see 2 things at one time. Wherever the OH goes, well, that's where the halogen goes. All right, so there's part B, and there's the answer. Let's take a look at part C. Part C, we had CH3 with a carbon, and then we had a CH3 up here, and then a CH3 down here, a CH with an OH there, and a CH3. And we're going to react that with HBr. Now, I'm leaving off heat. I shouldn't be doing that, but heat was pretty much in every single one of these, except for tertiaries. Tertiaries react very well. We don't really need heat for those, but, you know, just to be consistent, we often write the triangle there as well, just because everything can stay the same. It makes it easier for us. But, you know, I do leave these off quite often. All right, so I'm going to take this alcohol. I'm going to react it with HBr with a little bit of heat, and I want to know what will form. All right, so just like before, I'm going to take CH3, my carbon, my CH3, CH3, CH, OH, and CH3. I redraw the reagent. I do this every single time. So this alcohol right now, like we said before, is a secondary alcohol. There's a carbon to the left and a carbon to the right. It makes it secondary, which means this is going to be an SN1. So this carbon's not going to cheat. What that means is that in this type of substitution reaction, this alcohol group is going to leave. It gets protonated with the HBr from the H. It gives a black eye, bam, and then it leaves. So what it leaves behind is a carbocation. So that carbon looks and says, is there a better spot? If I go right-handed, this carbon's only attached to one other. That is a primary. That is not good for me. I'm not going to move in that direction. And then if it moves left-handed, it says, whoa, look at that. I mean, that carbon right now is attached to 4 others. I'm just asking for a tertiary spot. I'm not asking for a mansion. I'm just asking for a better place to live than where I'm currently at right now. So that carbon does see the left-handed carbon as a possibility. The problem is that it's attached to 4 others. But like we've said before, If we move a carbocation, folks, we have to switch it with something. We can't just move it over and leave everything over there. So if we do move it left-handed, it has to switch. Typically, they're hydrogens. Hydrogens are always disposable. Nobody likes old hydrogen. You know, again, I feel sorry for it. But this had no hydrogen to switch. What it does have, though, is a methyl group to switch, and that's a CH3 group. So carbon is going to get its way. Carbon looks left-handed and says, that's where I want to be. That's where I want to be in life. But in order for me to get there, something's standing in my way, and I'm going to take care of that in any which way possible that I can. Okay, well, job promotion comes, lottery winnings come, who knows, maybe they steal something from somebody. Who knows today? And that carbocation will switch, but it will switch with one of these CH3 groups. I'm just going to choose the one that's pointed down below. It doesn't really matter. They're all kind of the same, right? And this carbocation will now switch over and move. This is what we call a 1,2 methyl shift, and this is something that should have been presented in Chemistry 251. Now that that carbocation has shifted, we have a new spot, and that carbon feels really good about where that carbocation is at now. So that molecule says, okay, I'm ready. I'm ready to bring in someone in my life. I've improved myself. I'm in a better spot than what I was before, so come on. And this bromine is still out there swimming, and that bromine will go in, and it's attracted to that carbocation, and that's where the bromine will end up. It's right there, folks. That's where it goes. So 1,2 methyl shifts happen because we have a tertiary carbocation that's more stable than a secondary carbocation. If I want to name these molecules, I can. So I pick out the longest carbon chain, and it's going to be 4 pretty much all the way across. So this is a butane, but I'm going to drop the E, and I'm going to add the OL, butanol. And this is going to happen on carbon number 2. If I put the preference on the OH group, I give that the lowest number possible. Forget about everything else on the molecule. All right, then at carbon number 3, I have a methyl that points up and a methyl that points down. So this is going to be a 3,3-dimethyl-2-butanol. My product that I've ended up with down here at the bottom, again, it's 4 carbons all the way across. That's the longest chain. So this is a butane. And it looks like most of my substituents this time are over here on the left-hand side. Halogens, methyl groups, those kinds of things are pretty regarded as even groups. So on carbon number 2, I have a bromo group. I'm going to list that one first because alphabetical order. And then on carbon 2 and on carbon 3, I have 2 methyl groups. So dimethyl. So I've taken, listen up, I have taken 3,3-dimethyl-2-butanol, and I have reacted it with hydrobromic acid. The hydrogen from the hydrobromic acid has protonated the OH alcohol group. That protonated alcohol group now is a very good leaving group, and that decides to leave in a SN1 reaction mechanism. That frees up a carbocation. That carbocation will then undergo a 1,2 methyl shift, and that 1,2 methyl shift goes left-handed onto a tertiary carbon. The 1,2 methyl shift now allows the nucleophile of bromine to come in and attach, making 2-bromo, 2,3-dimethyl butane. How's that, folks? How's that for organic? Now, something else I'm going to weasel in here is this whole concept of stereochemistry. Not yet, but we will begin to weasel because we're talking about SN2s and SN1s, and going through the back door is very important as far as stereochemistry is concerned. At this point, they've not really done anything to me to show me stereochemistry, so I've not really had to tackle that, but they will. They will. And SN2s and SN1s are the driving force behind what happens with those particular types of products. So we'll eventually get there, just not yet. All right, so now we've got one more, and that one more is going to be part D. All right, so for part D, they give me yet another ring to make me feel intimidated, but it's not going to work, is it? And then off of this, we have a CH3 group. And then off of that ring, we have a CH that's here, and a OH that's pointed up, and a CH3 that's there. And we're going to add HCl. They want to know what would form. Not a big deal. We used what we did in A, B, and C in order to do this one. What do you think I'm going to do first? What should you do first? Well, if you said, write down the reagent, you're correct. Good for you. There's my ring, and here's the CH3 group, and then here's my CH with an OH group and a CH3 group. Now let's think about the steps here. I have an alcohol. I have an acid. The acid's going to go in and bam, give OH a black eye. And that OH group is going to leave in form of water. It leaves behind a carbocation. That is a secondary carbon. We've already talked about that, right? Secondaries, which means free carbocations will form. Rearrangement can take place because this is an SN1 reaction at this point. So if it goes left-handed, this is primary, or right-handed, it's primary. It doesn't want to do that. That's going backward in life. It doesn't want to do it. You don't want to do it either. If it goes left-handed, folks, it's going to move to this carbon at that position. This carbon right now is attached to 1, 2, and 3 carbons. That's a tertiary spot. It wants it. Well, that fourth bond right here is to a hydrogen. It's not drawn, but it's understood to be there. Those carbons have to have 4 bonds. So I told you that when carbocation shift, things have to switch places, right? And we are going to get a carbocation shift here. That carbocation is going to leave this secondary spot, and that carbocation is going to move here. Well, for that carbon to take the carbocation, it's going to have to take the hydrogen because, again, they're very disposable, and it's going to shift them over to where that carbocation was. A switcheroo has to happen. And now we have a rearrangement. This was called a 1,2 hydride shift. Now the 1,2 hydride shift is taken place. That carbocation now is ready to accept a nucleophile. And that nucleophile, folks, it's whatever was left over from the HCl. And that in that case, it was a chlorine. So chlorine is going to go on to that spot, and that will be the new location. There you go. So just like before, we have to protonate the alcohol. Once we protonate the alcohol, it turns into a very good leaving group that leaves in the form of an SN1 reaction. The carbocation that forms undergoes a 1,2 hydride shift. It moves inward to the ring structure. That's where the carbocation will stay. And then it gets chlorinated at that position. There you go, folks. There's the examples for A, B, C, and D. Now, I told you before, stereochemistry is going to be very important. So here's another type of question. Problem 8. What stereoisomers does the following reaction form? Okay, so I see these stupid little solid wedges and dashed wedges again. Anytime I see those, I start to panic, right? And you probably do too, because it's like, oh no, they want something about stereochemistry, shapes, and all of this other R and S kind of crap. And the answer is, yeah, they do. That's what they're after. That's also what this term stereoisomer means. So now we're going to have to go back, and we're going to have to think about not only substitution reactions, but this whole concept of stereoisomer as well. What on earth do they want me to do here? Okay, so here's the thing that you have to keep in mind. As before, I always start with my reagent. So redraw that. It's not going to change drastically from it, right? So here's my solid wedge, and here's the dashed wedge. Here's my OH, and there is the, sorry, not a hydrogen here. That was silly. That points over to a methyl group because they didn't write a hydrogen. It's understood to be a methyl group, CH3. So they want me to add HCl and a little bit of heat. Okay, so this is not a problem. I mean, right here, this OH group is attached to a carbon, and that carbon has one to the left, one up above, and one to the right. So this is a tertiary carbon. So tertiary carbons undergo a SN1 reaction. All right, so what does that mean in terms of stereoisomers? Well, stereoisomers, SN2s, they have to cheat, so therefore they have to go through the back door. Really what that means is that Walden inversion will take place. Walden inversion was a reaction that allowed a molecule to sneak through the back door, but if it does, everything flips, everything changes. So what was S is now R, and what was R is now S. Those stereoisomers will flip back and forth. So R to S and S to R. That's Walden inversion. That also means that if I have dashed wedges, they're now solid, and if I had solid wedges, they're now dashed. Well, because SN1 is here, SN1, well, it doesn't necessarily do Walden inversion every single time. It can, but it doesn't have to, because carbon is not a cheater. Carbon can make the decision to have something sneak through the back door. That's not a problem. But carbon, because it's single, can also allow people come through the front door. That's not an issue either. So what that means is that sometimes you will see a flip, and sometimes you will not see a flip. And that is what SN1 is all about. So again, SN1, because it's tertiary, that means that this OH group is going to get protonated. Bam! It makes it ugly. That hydrogen goes on, makes it leave in form of water, and chlorine will come on instead of the OH. So check, this is one option. Yes, that is one option. The orientation of the OH stays the same. It started to be a dashed wedge. It ends up being a dashed wedge. That molecule came through the front door. Again, it can do that because carbon's single. No sneaking. All right, well, the other option here is that because it's SN1, folks, you can still sneak through the back door. So that OH group is still going to get protonated, and that makes it a very good leaving group, and chlorine still goes on in its place. No rearrangement's going to happen. Tertiary spot. But it could have went through the back door, not the front. It's just kind of randomized in a way. Well, if it does that, this started off to be a dashed wedge. Well, now we're going to have to write a solid wedge because it came through the back end. Walden inversion took place. So both of these are going to be in existence. I'm going to get both of these as a product. So that's a very easy way to kind of think about, hopefully, the stereochemistry between SN2 and SN1s and in regards to the alcohol group. All right, so let's look at another one. What stereoisomers do the following reactions form? So the only one I want you to attempt right now is A and C. That is it. For part B, they're using reagents we haven't talked about yet. And for part D, the same. They're using reagents we haven't really talked about. These are different types of alcohol reactions, and we haven't made it that far. But for part A and part C, we can do that. It's an alcohol, we react acid, and for C, an alcohol reacting with an acid. And they want me to report stereoisomers. So because we've already introduced it, I'm going to skip ahead a little bit to a future example problem, and I'm going to pull part A and part C out, and we're going to answer those now. So, at this point, take a stab at them. Jot these down. try to predict the product. What do you think would happen? And then come back and we'll talk about them. So in the next video, I'll give you the answers for part A and part C, and you can cross-check those with your answers to see if you answered them the correct way. So good luck. I'll see you when you push play on the next one.